Okay, we're going to try to review how we assess, or methods we can assess ventilation and oxygenation, just to get us all on the right page. Remember, in our pulmonary system, we have capillary blood flow that goes around each alveoli. And as the capillary goes around, CO2 is diffusing into the alveoli, whereas O2 is diffusing out of the alveoli. So that is how it's normally supposed to work. So we are going to review methods to assess, to determine if it's not working correctly and what the problem is. Okay, so here we have a picture of a normal alveolus and a normal capillary bed. Remember, inside the alveoli, the PaO2, we use this equation here. So we have the PaO2 is equal to barometric pressure minus the water vapor pressure, and then your PaCO2 divided by your respiratory quotient, which is 0.8. Your PaCO2 in your alveoli, we assume it's equal to your capillary PaCO2. Since it's diffusing from the capillary into the alveoli, we assume that it's doing that until it reaches equilibrium. So that's the value we would use for PaCO2. Then in the capillary, we draw arterial blood gases to determine the PaO2 and the PaCO2. Okay, so that's how it's normally supposed to work. Now let's take a look at the two ways that it cannot work correctly. First, we have shunting. Okay, this is where there is an obstruction to the alveoli in some form. So the alveolus is not getting ventilated, but we do have perfusion. Okay, so we do have blood flow going around the alveoli, but we do not have air ventilating the alveoli for some reason. Okay, the calculation we use for this is a shunt equation right up here. We need our PaO2, our P big AO2, and our PaO2. You also need your Ca minus VO2, which if you don't have that, if you don't have a pulmonary artery catheter to get your SVO2, or CaVO2, excuse me, you're going to use 4.5 for that part of the equation. And then there's the rest of it there. Okay, typically, if you notice down here on the table, it kind of shows you which values are going to be affected by each. Typically, with a shunting problem, you're going to have a major effect on your PaO2. It's going to be significantly decreased down to, say, 40, when normal PaO2 from your blood gases should be 80 to 100. So your PaO2 is going to be majorly affected here. Okay, our next one is our dead space. Dead space is when you have an alveolus that's being ventilated, but you do not have perfusion. The blood flow past the alveoli is being blocked. So you don't have any perfusion, but you do have ventilation. Here is your equation to calculate dead space. And notice your big problem then with this is going to be your PaCO2. You're not going to have ventilation, and your oxygen will also be affected. Both of them will be affected, but typically when you're talking about dead space, we're talking about a ventilation problem, and when we're talking about shunting, we're talking more about an oxygenation problem. Okay, I'm trying to keep it simple and just focus on the facts here. Okay, so we've used these terms. Now, what do those really mean? Okay, over here is a picture of the physiological dead space. So everybody, this is digging way back in our memory here. The trachea and conducting airways are your anatomical dead space, and then you have your functional dead space, and this is where there's no gas change because you have no pulmonary blood flow. Okay, that's the dead space I was talking about on the last slide that we're going to try to calculate in some situations. Your minute ventilation is the total air moved in and out, whereas your alveolar ventilation is what's actually being exchanged in the alveoli. Okay. So next we have our interpulmonary shunts, and there are three predominant types. The first type, or I believe they call it the true shunt, is when a pulmonary capillary doesn't even go past the alveoli, like this blue vessel right here. Okay, that is a true shunt, so it never even comes near an alveoli, so no gas exchange can occur. That is deoxygenated blood going from the right side of the heart to the left side of the heart and delivered out to the body. So that's bad. Then we have two other types. An example here, this alveoli has a thickened AC membrane, so diffusion is impaired. Okay, that's another type of shunt. And then over here we have consolidation in an alveoli, like pneumonia or whatnot. And again, diffusion cannot occur because it can't get through the consolidation into the capillary. So those are your three types of shunts. So those are the things we're covering in this video. Just to remember, because we're digging way back here, we start at the right side of the heart. The blood comes into the right side. If we were to measure that blood as it goes to the lungs, we would be measuring the PVO2, the venous content, and the SVO2. Okay, after the air leaves the lungs going to the left side of the heart, it should be fully oxygenated, and so our PaO2 should be about 100 and our SaO2 should be about 98%. Other components that make up our ability to oxygenate is our hemoglobin. Normal hemoglobin should be around 15. As we keep following around, we see cardiac output plays a role in this. Normal cardiac output is 5 liters per minute, and that is affected by heart rate and stroke volume, and those are affected by preload contractility and afterload. Then to calculate the actual O2 content in our blood, you have these formulas here. Normal is around 20% volume. Then we talk about delivery down here. This is what's actually getting to the organs, your DO2. And you have your calculation there. Should be about 1,000 milliliters or 1 liter per minute there. And then we have at where respiration actually occurs, okay? Gas exchange at the organ level. And then the blood enters back into the venous system. And so here is our VO2 and our calculation for that. Normal is about 250 milliliters per minute. And then our venous content. Again, you need your hemoglobin for that one. And then we go back to the heart. So this is just showing you again how where each measurement's coming from. When we do calculations, it's easy to plug in the numbers and find an answer, but then to think about, oh, what does that number actually mean? So I need pictures to help me keep it all organized because I have a lot going on in my brain. So this is just to help you keep it organized. Okay.